A earthquake P and S wave time travel chart. What we're really looking at is the speed of the S and P waves, because speed is distance over time. How far, so speed is equal to distance, and in this case we're looking at the epicenter distance, so the distance to where the earthquake started, epicenter. Distance divided by time. And the travel time is the time that it took for these waves to travel. So distance divided by time is speed. So this graph is showing us the speed of the S waves and the speed of the P waves. And you can see here, when we look at the lag time, then we're looking at the difference between the S speed. When we're looking at the lag time, we're really looking at the difference between the time that the S and P waves arrive, the difference, time difference. So if I went back and looked at the lag time from the example, which was 1.5 minutes. So what I'm going to do then is find 1.5 minutes on this graph. And this is 1 minute, so this is 1.5 right here. Distance, and find out where that distance is on this graph. And let's just say this measures the length of the post-it note. Okay, so I'm going to try to find on this graph the distance between the S and P waves that is equal to this distance. Right here, it would not work, right? So where would this fit? Okay, so I'm going to say right here. Now if we look at that, what does that tell us? That tells us the distance to the epicenter of the earthquake. Now these numbers, though, have to be multiplied times 10 to the third power. Okay, so we're going to say this is not half. It's a little more than half, so I'm going to just estimate. I'm going to say it's I'm going to say point. Okay, so here is scientific notation, and so we're going to move the decimal 3 places to the right. 1, 2, 3. All right, and that's going to give you 600 kilometers. So this then is the distance to the epicenter of the earthquake. And I would use then the triangulation method to figure out where the earthquake is actually located. Because this just tells me, right, if this were a size in the graph right here, this just tells me the earthquake is 600 kilometers away. But I don't know if it's over here, I don't know if it's there, I don't know if it's there. I don't know where it is. I can know it's 600 kilometers, but it could be anywhere. Woo! Right, so we have to use triangulation to narrow it down. Then, if I want to figure out if the lag time is 1.5 minutes, and let's say the P waves arrive at 6 a.m. in the morning. So we're going to say 6 a.m. we have P waves. If the lag time is 1.5 minutes, then then the S waves arrive. So P waves and then S waves. Because the lag time is 1.5 minutes. Okay. But I want to figure out, when did the earthquake actually happen? Speed is equal to distance divided by time. So the distance to the epicenter, I calculated, remember I used the lag time to figure this out, and we said that was 600. So D is 600 kilometers. If we're at 600, what is the time? So where is, and let's just say that's 1.5 minutes. So the time it takes to go 600 kilometers is 1.5 minutes. So what is the speed then of the P wave? Distance divided by time. So distance, 600, divided by time, 1.5. Remember, it's distance divided by time per minute. So if we want to figure out what time this earthquake happened, here's the time the P waves arrived, the seismograph. This does not mean this is when the earthquake happened, though. Right? This is the time the S waves arrived. So the distance we calculated to the epicenter is 0.6 times 10 to the third, so 600 kilometers. And the time it takes to go that distance, for the P wave to go that distance, is 1.5 minutes. So it takes 1.5 minutes to go that distance. So then we just work backwards. So if the P waves arrived at 6 a.m., 1.5 minutes before that is when the earthquake happened. So this is when the earthquake actually happened. It happened 1.5 minutes before the P wave arrival time. Because that, we can see, that's what we get using this table, using this graph.